Bueno, hoy tenemos a Oscar García Prada. Sorry, in English for the outsiders. For the people that is joining us online, today we have, well, what was my PhD advisor. I'm very proud of that. And a friend who is Oscar García Prada from ICMAT and CSIC, which is the Council, the Spanish Council of Research for Research, and specifically mathematics. He's going to talk us about higher rank Teichmüller spaces and Higgs bundles.
Well, thank you very much, and the honor is all mine, in particular to be starting this YouTube channel, this YouTube seminar. So thank you very much for the invitation. And let me tell you what I would like to do in this talk. I want to give a full classification and a complex algebraic parametrization of what we call higher rank Teichmüller spaces of a compact real surface using the theory of Higgs bundles. This will become hopefully clear through the talk. And in a sense, this work that I'm going to present today is actually the culmination of many of the works, but in particular the last the fundamental work that I will present today is the culmination of work of many mathematicians, many people in the last more than 30 years, and in particular starting with the seminal paper, one of the seminal papers of Hitching, where he links to Teichmüller theory, this paper on Lie groups and Teichmüller space in 1992. Let me start with then a compact surface. This is just a surface, not complex structure or anything. This is, for the moment, it's an oriented, smooth, complex surface of genus bigger than 1. And we're interested in a fundamental group of S. And then we consider a complex semi-simple reductively group, G. And the emphasis will be on a real form of this complex semi-simple group. I won't be writing too much in the Blackboard, but I want to just clarify what I mean by that. And what I mean by a real form is I have sigma, which is an anti-holomorphic involution of the group. So anti-holomorphic involution. I can equally think of this at the level of the Lie algebra, antilinear involution, and then by the real form, GR, what I mean is actually the fixed points of this fixed points of the action of the involution in G. For example, if you have SLNC, you have SUN, for example, or SLNR, or SUPQ, and so on. There's a classification of these things. And what I want to emphasize, and this will become clear, it would be used quite a lot, is that in studying real forms of complex simple groups, you can either think in terms of anti-holomorphic involutions, right, or holomorphic involution, curiously. So, and the reason is that Cartan says that if I give you a anti-holomorphic involution, there exists another anti-holomorphic involution, tau, right, of the group that defines the compact real form, right? So that G tau is a compact real form, like SUN, for example, for SLNC, compact, and that commutes with sigma, so such that sigma, tau, sigma are the same, and then I call this theta, and this now is a holomorphic involution because I am composing two anti-holomorphic involutions. So I can think of real forms of an anti-holomorphic involution or this holomorphic involution, thanks to the existence of this unique compact involution that commutes with a given one. Okay, so this is what I mean by a real form, and we have some examples in mind. As I said, the emphasis is in actually non-compact real forms like SLNR or SUPQ and so on. And then we want to study representations of the fundamental group of S into this real form. And by the way, let me emphasize that a complex group is itself a real form. A complex group is in itself a real form of G is a real form of G cross G with a certain evolution. So what I'm going to say covers also the case of complex groups, except that, as I said, more interest is in groups that are real forms but are not complex. Right? But all the theory that I'm going to present is equally valid for complex groups. And so I want to study representations, that is homomorphisms of the fundamental groups in GR. And as usual, we are interested in equivalence classes. And the main point when you consider GR a non-compact is that you cannot take all the homomorphisms. You have to restrict yourself to what we call reductive representations. And these are homomorphisms, so that if you compose with the adjoint representation to the algebra, that representation, the composition, decomposes in direct sum of irreducible representations. Right? And so those are the good ones that give us a defined moduli space. We call the moduli space of representations or character variety, GR character variety, as the set of equivalence classes of reductive representations. And so this set has a very nice structure as an real analytic variety, complex if GR is complex, and it's actually algebraic if GR is algebraic. Maybe sometimes you have to be precise and say it's semi-algebraic, but let's not enter into this delicacies now. And so you can attach an invariant to such a representation, and one way of attaching this invariant is by realizing this important equivalence between representations of the fundamental group. This is actually true for any manifold, right, of any dimension, and isomorphism classes of flat GR bundles. So GR bundles with a flat connection, right? And so if we assume that GR is semi-simple and connected, then these flat GR bundles are classified by the second cohomology of S with values in the fundamental group of the group GR, and this by, S is a surface, so this is isomorphic, and the fundamental group of the Lie group is always abelian, so this is isomorphic to the fundamental group of GR. So the invariant is an element in the fundamental group of GR. Right? And then we can then fix the invariant of the representation, being the invariant, this element in the fundamental group of GR for the corresponding flat bundle. And when we fix this invariant, we can consider a subvariety of the character variety, where we are fixing exactly this invariant to BC. We call RC, fixing this. And it's important that when GR is compact or complex, the number of connected components of this variety is exactly classified by the fundamental group of GR. So this invariant here classified counts components. Right? And so, for example, for SLNC or SUN, because it's simply connected, there is only one component in the character variety. Right? For any simply connected group, there's only one component. But the situation here is very different if you take non-complex, non-compact real groups. So real forms like here, but they are not complex, right? And so in this situation, the map that associates to a component this invariant is neither subjective nor injective. And the fundamental example that I want you to consider today, and this is a seminal example, not just for this aspect of components, but actually for the Teichmüller aspect, is the group SL2R. This is the prototype, the non-abelian, non-compact real form, SL2R, real form of SL2C. And in this case, because the SL2R retracts into SO2, the circle, then the fundamental group is actually the integers. So the invariant in this case is an integer, it's called the Euler number. Right? And then once you fix this Euler number, you have this subvariety that I will call here RD, the subvariety of the character variety with fixed Euler number T. And is a very old result of Milner that this variety here, subvariety is empty unless the Euler number is bounded by the genus -1 in absolute value. So this is telling you that the map that I was describing before, this map is certainly not surjective. You have to, there's this bound, right? Very important bound that has to be satisfied. And then, you know, like 30 years later, Goldman and Hitching with different methods actually proved that if you fix this, the Euler class is smaller than G-1, then this is connected. But if you take the maximal value in absolute value, then there are 2 to the 2G connected components. So then this map is not injective either, right? So this is exactly the prototypical situation. But more importantly, and more relevant somehow for this talk, is the following fact that these components, remember there are 2 to the 2G components when you fix the D to be G-1 or the opposite. Each of them actually consists entirely of what we call Fuchsian representations. These are representations that are discrete and faithful. And so these representations, via the uniformization theorem that relates hyperbolic metrics with constant scalar curvature to complex structures, is actually can be identified with Teichmüller space. So each of these, so is a, you know, people working on Teichmüller space very often do not think of Teichmüller space in this as a component of the character variety. But for this topic, this is crucial. So the Teichmüller space, actually, in fact, we have 2 to the 2G copies of Teichmüller space once we fix the Euler number to be G-1. And excuse me, discrete. What does discrete mean here? Discrete, it means that it is just, you know, this is inside SL2R, right? So this that's really the topological instance is a discrete set, yeah, and it's injective, right? So you're putting the group in exactly in the most favorable way, and there's a yeah. So in the other components, you do have discrete representations, but not all of them are discrete, right? In this particular case, all the representations are discrete. This is the characteristic of Fuchsian representations, and in fact, how you, from the uniformization theorem, you get the Riemann surface, you recover the Riemann surface as the quotient of the upper half plane, let's say, by the action of this group. Yeah? So this is, yeah, that's how uniformizes. Yeah? Yeah. Any other question? Okay, so then what I want to show today is that there are higher rank simple groups, GR, different to SL2R, whose moduli space of representations has also connected components consisting entirely of discrete and faithful representations. And this actually is the subject of this higher technology, right? And so we want to give a full classification actually of what are the groups for which we have this kind of components, right? And from the perspective of complex algebraic geometry, from the perspective of Higgs bundles, and also not only classify them, but also give a parametrization in holomorphic terms, as you will see. And this program involves two theorems, two correspondence theorems. The first one is the non-abelian Hodge correspondence that I will explain, and the second one, so the first one, non-abelian Hodge correspondence, is relating representations of the fundamental group of S into the group in terms of holomorphic objects on the Riemann surface. So we have to choose a complex structure on the surface S, and to make it a Riemann surface with a projective complex smooth composite rank curve. And the second one, once we have that correspondence, involves another correspondence, which is specific. This one is actually true for any real form. This one is a specific, what we call Cayley correspondence, and is actually specific of this particular class of groups, yeah, that we will describe. All right. So to give you describe the non-abelian Hodge correspondence, then I need to talk about Higgs bundles. And now we choose on the surfaces a complex structure, and X, I call X the resulting compact Riemann surface. And so now I have the same ingredients. I have G, complex semi-simple Lie group, a real form, and now I need to distinguish a maximal compact subgroup of GR. And then this maximal compact defines me what is called the Cartan involution and then the Cartan decomposition, which is that the Lie algebra of this GR decomposes as the Lie algebra of maximal compact and the orthogonal part by the Killing form. And this satisfies these important symmetric pair properties. Here as an example, SLNR, right? Maximal compact is SON, right? And so you have the SLNR, the Lie algebra, decomposes the Lie algebra of SON plus this symmetric matrices here. Okay? So this is, you have this for any real form once you have chosen a maximal compact. Now, a very important ingredient in here is the isotropy representation. So this is a representation of the maximal compact into this orthogonal part. I mean, if you restrict the adjoint representation of GR of this group into its Lie algebra, it gives you two representations: the adjoint representation of this group and this other part. And this is the isotropy representation, which we complexify by taking, actually H here is the complexification of this compact group, and M is the complexification of this vector space. Right? And so these are all the ingredients you need now to define Higgs bundles. And so here is what a Higgs bundle is, what we call GR Higgs bundle. On the Riemann surface, it is a pair consisting of a holomorphic principal H bundle. H, remember, is a complexification of the maximal compact of here. And then what we call the Higgs field is a holomorphic section of this vector bundle here, is the vector bundle associated to, so is an H bundle, and because we have a representation in M, we can construct this vector bundle with fiber M, and we can tensor it by the canonical or the cotangent bundle of the Riemann surface, and so this Higgs field is a section of this vector bundle. Okay? So if you apply this to GL and C, for example, or SL and C, you recover the old concept of Higgs bundle introduced in the first paper of Hitchin as a vector bundle with a fixed determinant, trivial determinant, and an endomorphism of the vector bundle tensored by the canonical with traits in zero. So this generalizes that notion, the initial notion introduced by Hitchin for complex groups in particular. And so there are appropriate notions of stability and so on in the sense of geometric invariant theory, and one can construct these moduli spaces and prove that they are complex algebraic varieties, non-compact, complex algebraic varieties. And there are several constructions. The most general, suitable for our purposes, is the one given by Alexander Schmidt, for example, which covers actually other objects, but in particular these ones. So we have this construction of these complex algebraic varieties using geometric invariant theory, and it is important to remark that the canonical line bundle here could have been replaced by any line bundle, and this is not just a generalization comment. This will play a role in the talk. We will consider objects in which actually you are tensoring by another line bundle, typically a power of the canonical bundle. Okay, and okay, so, and we will specify the line bundle, unless it is the canonical bundle, in which case we just drop the L and we just call it the moduli space. Right. So any questions about this moduli space of Higgs? So why do we care about these things? Is exactly the non-abelian Hodge correspondence. And the non-abelian Hodge correspondence tell us that if you consider the smooth compact surface S, as we did at the beginning, and you orientable and so on, and you fix a complex structure on S, then you can identify there is a homeomorphism between the character variety and the moduli space of GR Higgs bundles for any complex structure. This is always true. And this actually, the proof of this correspondence involves two existence theorems. One is some solutions to Kitching equations. Since this is a seminar on mathematical physics, also these equations actually appear as from the Young-Mills equations, and sometimes are referred as Young-Mills equations on Riemann surfaces, or but these are dimensional reduction of the instanton equations. And anyways, there are some gauge theoretic equations that one needs to solve, and that is one theorem that is proved in different degrees of generality, as I explained there. And then another theorem, actually, that is that if you give me the representation, and remember, we could view this as a flat GR bundle, so a GR bundle, principal bundle, a smooth GR bundle with a flat connection, then I can find what is called a harmonic metric, which is a reduction of a structure group to the maximal compact of GR. Here, the Kitching equations are also a reduction of the structure group to the maximal compact of H. And H and GR shared the same maximal compact. Because HR was the maximal compact of GR, but also H was the complexification of HR. So that is actually the link, if you want. As in the case of representations, we can also attach a topological invariant to the Higgs bundle. And this is nothing but actually the topological invariant of the principal H bundle, and these are classified in a similar flavor as before by the fundamental group of H, which because HR is a maximal compact, H retracts into HR, and this is just the fundamental group of HR. The same exactly, which is the fundamental group of GR, because both, as I said, both retract. H and GR retract into HR, right? And so it's the same topological, the same kind of animal. And so it's an element in the fundamental group of HR. And of course, by fixing this invariant, we can consider also the subvariety of Higgs bundles with this fixed invariant. And no surprisingly, the non-abelian Hodge correspondence identifies this also the corresponding character variety of the moduli space of Higgs bundles with fixed invariant. So this is the non-abelian Hodge correspondence in a nutshell. And now I want to tell you about the other correspondence. And as I said, this correspondence, the non-abelian Hodge correspondence, is actually valid for any group, any real group. I said the simple real form is actually true for reductive groups in an appropriate sense. I have to generalize appropriately. You may need to consider a central extension of the fundamental group or something like this. But what I'm going to tell you now is specific for certain groups. And so this is the Cayley, what we call general Cayley correspondence. And this is given in my work with Steve Bradlow, Brian Collier, Peter Gothen, and Gothen and Oliveira, in a paper that this has appeared already, is about to appear. And so to describe this correspondence, this is a bit of Lie theory. So G is a simple complex Lie algebra with group G, and we want to study nilpotent elements. And let me remind you that an element in the Lie algebra is said to be nilpotent if the adjoint representation of that element, which goes from G to G, is an important matrix, is an important endomorphism. So this is the definition. And an important property is that the nilpotent elements of a simple Lie algebra are a cone. You can multiply by a non-zero complex number, and you get also an important element. And this cone here has a finite number of orbits under the action of the group G. G acts on the Lie algebra by the adjoint representation, and there is a finite number of orbits in this nilpotent cone. There is a distinguished one, which is called principal orbit, and the nilpotents there are called principal, and this is the unique open dense orbit. Principal orbit, principal nilpotents. This plays an important role in representation theory, in symplectic geometry, and so on and so forth. Now, nilpotent elements, there is a correspondence, thanks to the Jacobson-Morozov correspondence, that if I give you an nilpotent element that's different from zero, right, you can complete it by adding another nilpotent element F and a semi-simple element H, so that they satisfy the relations of SL2, right? So this is what is called an SL2 triple. Study of SL2 triples in Lie theory is a fundamental, because it's a strategy to reduce problems in Lie theory representation to SL2, which is the most basic example, right? And so this the theorem of Jacobson-Morozov says that there is a bijection between the nilpotent orbits, so nilpotent cone modulo the action of the H group, and the subalgebras. So once you have this triple, they generate an SL2C subalgebra, right? And so there is a one-to-one correspondence between conjugacy classes of nilpotent elements and conjugacy classes of SL2 subalgebras, right? And now, if I want to tell you about some, though I mentioned there is this special class of nilpotents called principal. These are the nilpotents in the open orbit, open and dense orbit. But I want to tell you about other distinguished orbits that somehow appear in the game, and we call magical SL2 triples or magical nilpotents, the elements that are in these orbits. Let me explain what is such a thing. And so, if I give you a nilpotent element, am I repeating this? I think I'm repeating this. Yes, for some ridiculous reason. Anyway, now if I give you a non-zero nilpotent element, right, E, I complete it to an SL2 triple, and then the SL2 subalgebra that it generates. And once I do this, I have two different decompositions of the Lie algebra G. The first decomposition that I have is as an SL2C module. So SL2C acts. This SL2C acts on G, and so G decomposes. We study representations of the algebras and so on. This is the first non-trivial example that we study, right? Representations of SL2, and so we know that every representation, in particular, if you take as a representation G, right, decomposes as SL2C modules, and you can every WG that I have here is NG copies of the unique J plus one dimensional irreducible. In other words, I can decompose in whatever number of copies of irreducible representations. Okay, this is one decomposition, very basic in the Lie theory and the study of representations of this SL2C in G. And then there is another decomposition. Once I have this element H, I can remember it was a semi-simple element. I can consider the adjoint action of this element, and then I can decompose the algebra in terms of eigenspaces. So this element acts on X by eigenvalue J, right? And the GJs are exactly this, the ones that the eigenspaces corresponding to eigenvalue J. And notice that the at E moves this like 2, right? It's like a creation and in particle physics creation operator, and or this other, sometimes this is actually appears in that context. Huh? And the joint action of F goes from Gj to G minus 2. So these are 2 decompositions that you have of your Lie algebra, both of them very natural and clear, I think. And then you can sort of combine them to the point that I can write everything in terms. I can decompose G in terms of the highest weight subspaces that I have that describe the reducible representations. And I can basically, by acting as many times as necessary with F, I can write at the end of the day everything in terms of this representation. This is really just nothing very serious, right? Okay, so once I have that, I can now define a vector space involution of this Lie algebra by to the important element by just saying, okay, on B0 you are the identity, and on these other pieces you are like this. You can check that this is truly an involution, so you compose twice and it's linear and so on. So there's a vector space automorphism of 2. But sometimes a miracle happens, and the miracle is that sometimes this is a Lie algebra involution, not just a vector space involution, right? And when that happens, we say that the important element of the SL2 triple is magical, right? And so then, indeed, remember what I was explaining here in the blackboard, how you relate real forms and holomorphic involutions. I mean, I did it at the level of the group, but this you can do at the level of the Lie algebra. It's anti-linear and so on. That you can, out of this, this is a linear involution of the Lie algebra, right? This theta when the thing is magical. And then I can associate to such a thing, to such an important magical element, a real form, right? By finding this, Cartan tells me there is this compact involution, and so I can go from this theta e to this sigma e, and I have my real form. Okay, so these are these magical important elements have some canonical real form attached to it. Now, the thing is, do these things exist? So here's the classification of this in our paper. One of the things we do is we classify these magical important orbits. Yeah? And an important ingredient that we use is what is called the famous Kosten-Sekiguchi correspondence that relates orbits. You see, this is the important cone in the real Lie algebra acted by the real group, and for some reason there is a correspondence between these orbits and the orbits of an important cone of this M by the action of H. So this is Kosten Sekiguchi, but it was proved by Sekiguchi and Djokovic independently. And so the transition between this, the way you prove this correspondence is by you give me some triple, it's called K triple, I give you a normal triple in G, and so on. So by using this, this is by now classical theory, real forms and the symmetric decomposition, we get the classification of magical important elements, or if you want also, what are the real forms that do appear in the picture, right, as canonical real form associated to some magical SL2 triple, right? So the classification of this magical SL2 triples is as follows. For G of any type, yeah, any simple Lie algebra, you always have the split real form appearing. Split real form means, for example, SLNR for SLNC and so on. That every complex, every complex Lie algebra, complex group, symbol has a split real form, right? And precisely this real form appears from the principal nilpotent. It so happens that the principal nilpotent is magical. But there are other magicals, and so the other other magicals that appear here, magical nilpotent elements, give rise to real forms that are what are called forms of Hermitian type and tube type. I will explain this later on. This is a class of objects that appear, and then there is also the groups SOPQ appearing attached to some other magical importance, right? And then finally, for these exceptional groups, we have some real forms appearing. These are called forms that are quaternionic real forms. These are called Hermitian real forms because the symmetric space associated to it is actually a Hermitian symmetric space. It's actually Collier. I will explain that. But in this case, the symmetric space, which is GR, the group GR modulo, the maximum compact, is actually has a quaternion Collier structure. So this is the whole classification of things, and it's important to observe that actually some real groups appear twice in this list. For example, this group, the symplectic or Lie algebra, the symplectic real Lie algebra, SP to an R, is also the split real form. But they do appear from other magical nilpotent orbits. These appear from the principal one. This appears from another kind of orbit. Right? And the same happens for F4, for example, and the same here in this list. There is SOPP or SOPP plus 1. Those are split, but they are also and they appear in this list. They feature, some real groups feature in that list because they appear as canonical real forms of different nilpotent, magical nilpotents. And the important point is that some real forms do not appear at all. Right? For example, G2 is not appearing in this picture. I mean, there are no. So, and these are indeed the real forms that will feature, and the corresponding groups that will feature in this higher Teichmüller spaces. Let me then go on this, and here is the Collier correspondence. There is a lot of Lie theory yoga in this story, and one yoga is that if you give me a magical triple, we can extract some numbers, some integers here that I write here, and actually a real form, yet another real form of this G prime algebra. This G prime is, remember that H had these spaces, GJs, that were the eigenspaces for the action of H, right? And this is the one corresponding, this is the G0. I rename it here, call it G prime, but this is the G0 that appeared in the second decomposition of the Lie algebra. And in the package, I do get a real form of this thing as well. So I cannot explain, I don't have time to explain how you get all this the yoga, but it's actually explained on paper in great detail. And so here is the thing. If you have a magical nilpotent with corresponding canonical real form GR, and if GR is a Lie group with such a Lie algebra, then there is a map called the Collier map that goes from the moduli space of, remember I told you that we were going to see Higgs bundle twisted by different length bundles. So this is the moduli space of Higgs bundles for another group, GR prime. Now, this group whose Lie algebra is this, and then there is some twisting by some power of K, right? And then you have a bunch of holomorphic differentials here, right? And the thing is that the image of this map is open and closed in NGR. So it's a union of connected components of the moduli space of our character variety. And this is what we call Cayley components. So they are obtained. There is a mechanism actually relying on this classification of particle importance, but also on the theory for SL2, like everything comes from SL2R, right? That gives you this map and between moduli spaces. And so let me, this is very general, but let me mention this Cayley correspondence generalizes previous constructions and giving a unified approach. And perhaps the previous constructions, the cases are more elementary to see. Like the first example is actually the construction given by Hitching, the paper that I mentioned, right? And Hitching in the paper that I mentioned in '92, right? Consider this is the complex group, like SLNC, let's say. And he considered a map that is called the Hitching map that is obtained by evaluating the Higgs field at a basis of the invariant polynomials, G invariant polynomials on G. And these powers are the exponents of the algebra, some canonical numbers appear if you give me the algebra. This vibration is very important in other contexts, in mirror symmetry and in Langland's duality and so on. But the relevance in the study of character varieties is that actually what Hitching did was constructed a section of this map by precisely using the principle SL2 triple. He didn't use the machinery of magical or anything or so on, but in effect, he proved, and we based our approach in his construction. He proved that for the principal SL2, that the principal SL2 hypothesis defined you a real form, and that this real form is this split real form, like SLNR or SOPP or something. Some canonical, the split real form that always exists. And then he constructed a section. This goes to the moduli space of G Higgs bundle. So these are in the character variety for the complex group. But he showed actually that factors, and that really lies in the moduli space of Higgs bundles for GR. And so this corresponds to representations of the fundamental group in GR. And this is the famous, it's called now Hitching components. And it was the first example of higher Teichmüller components. And it was a kind of a surprise to realize that this map is really a particular case of the Cayley map that we do in general. Because what we call Cayley map originally was for another situation. This is one case that was studied before. I'll give you another case. And this is the case of groups of Hermitian type, meaning that the symmetric space admits a complex structure compatible with the Riemannian natural structure. So this is the Kähler line, right? And then the story, I mean, SL2R happens to be split on the one hand, and it happens to be also Hermitian. That's why it's in both worlds. So in the Hermitian situation, if GR, let's say, is simple, what happens is that the fundamental group of HR is basically isomorphic to Z, meaning that sometimes there is some torsion. So the torsion-free part is isomorphic to Z. This is what happened, I mean, to SL2R. Remember, the fundamental group of SL2R is actually the integers. And so this is general, but except that sometimes, for some groups, GR of this type, you have some torsion. And so this integer is called in this context the Toledo graph. This is for Domingo. It was discovered here in Toledo or something, but I mean, obviously Domingo must come from Toledo somehow. But and so there is this inequality called the Milnor-Wood inequality that generalizes Milnor's inequality that says that the Toledo invariant is bounded by the rank of the symmetrical space times the genus -1. And there are proofs of this inequality using Higgs bundles that we gave over the years, starting with some paper more than 20 years ago, and then proofs in terms of representations. And this was the original proof of Domich and Toledo, and also for classical groups, and in general by Berger, García, and Binghart. So this is the Miller inequality for these groups of emission type. And if you consider the maximum case, remember this is what in the case of SL2R was giving you the Teichmüller components. If you consider the maximum case here, then you have this theorem that we was the first time we used this terminology of Cayley correspondence, where the maximal component can be identified with another moduli space, right, of K squared twisted Higgs bundles for another group that has a geometric interpretation of something very fundamental to the symmetric space called the Schiller boundary. I'll just not enter into that. And so you see, this is again an instance of the Cayley map that I was explaining in general. Both this and the heat change situation are sort of pure. If let me just go to back to the general correspondence. And in the heat change situation, is like this part here is not there. It's only this, right? And in the Hermitian situation, this part is not there, and it's only this. And these are two instances of this correspondence, and that identified this this special component called Cayley components. And then there was another. I mean, for several years, I don't know how we're doing time-wise. Oh dear. Should be spilling. Yeah. So for several years, it was believed that maybe split real forms or Hermitian real forms were the only ones that appeared in this higher Teichmüller story. But then it was sort of a surprise to realize that there was a story also for SOPQ, and some evidence came from different fronts. But actually, first front came from the thesis of one of my students, Marta Aparicio, who was studying this moduli space of SOPQ Higgs bundles and was trying to count components using the more theoretic methods introduced by Hitching. And I was very naively thinking that the topological invariant was there going to give you the components. And she was computing this Morse indices and so on, and realized that no, that was not like that. Maybe there were other components, or this could be in the closure of other, so it was not conclusive, right? But some years later, and then there was evidence coming from another front that I will explain later on. And in fact, the fact is that later on, when Marta was actually no longer in academia, we took over and developed the thing, and found that also in that situation, there is a Cayley correspondence, and the Cayley object is actually a sort of a mixture of the Hermitian case where you only have that, and the Cayley and the Hitching situation where you only have that. And you can, let me say, but what is the beauty of this kind of correspondences? First, you identify. First, I haven't said that these components are higher Teichmüller. I will come to that. Meaning that they are discrete and faithful representations, right? Entirely. But already realizing that you can go from SOPQ to a group like SO1 that has rank 1, right? And makes the study of the topology of these things much simpler, right? And that's one of the goals. We want to study the topology of these things, and also gives you a counting of these components, right? But all right, so these were, but now, why are this? So the claim is that Cayley components are higher Teichmüller components, meaning that they consist entirely of discrete and faithful representations. Higgs bundle theory alone cannot do that, cannot prove that such a thing. But over the years, so in the case of the split groups and the Hitching component, so the work of François Labourie, who introduced techniques from dynamical systems, and in particular introduced the notion of a Nosov representation. That is a notion, so is a Nosov representation for a representation of a fundamental group of S into some real group, and this involves a parabolic, the choice of a parabolic subgroup of GR. And so, and Nosov representations happen to be discrete and faithful, he proved, right? And so this is another pillar of the theory of François Labourie on Nosov representations. And so, combining the work of Hitching and the work of Labourie and then Fock and Goncharov and so on, one could prove that indeed the elements in the Hitching component consisted entirely of discrete and faithful representations. So they are qualified to be called higher Teichmüller spaces if that is the main property that we want. And then similarly in the Hermitian case, this was proved using the same Nosov story and the properties with Berger, Yotzi, Labourie, and Winhoff. Now, in general, so how do you prove this that these other components that we are constructing are actually higher Teichmüller spaces, in the sense that they consist entirely of discrete and faithful? This involves the theory of the positivity, the study of positive structures on real groups. This is a very interesting subject, and there is a notion of positivity on a real group that also involves a parabolic subgroup, right? And I cannot explain here the details of what it is, but let me tell you that it gives you a way of giving some kind of ordering. If you have triples, 3 elements in this flat variety, or tuples, gives some cyclic order, right? So it gives you some way of describing order. And so this notion that Guichard and Winhard introduced generalizes a notion of what is called total positivity that was introduced by Lustig in the case of the split real forms. And in the Hermitian case is also related to the Maslov index and so on. So there was something in the case of split and Hermitian groups, but this Guichard and Winhard found a general notion of positivity that involves this parabolic. You can say parabolic. What is the parabolic having to do? Okay, but let me not anticipate things. Now, then if you have this kind of positive structure, then if I give you a representation, right, of the fundamental group in this dynamical story or topological study, similarly to in our situation, Higgs bundles are the crucial things and so on. Here, an important ingredient is that if you have a representation, there is automatically a boundary map, something that goes from the boundary of the fundamental group of S, that you can view it as the boundary of the Poincare disk, right? Goes from the boundary of the Poincare disk to this flat variety, which in fact is a sort of boundary on the symmetric space, GR mod by HR. And positivity means that a representation is positive if there exists a raw equivariant map that sends positive triples, let's say on this one, 2 positive triples in the flat variety, or just more generally n triples. So now here is a well, more recently, I guess, in 21, just after a paper appeared, Guichard, Labourie, and Winhard proved the following. That this was known. That if you have positive structure on the group and you take a positive representation, then this positive representation is a Nosov in the sense of Labourie, so in particular discrete and faithful. The set of PR positive representations is open. This was known. It was very easy to show. It's open in the canonical variety. And then they proved that in this paper that the positive representations are not quite close in the character variety, but are close in a subvariety of this character variety consisting of irreducible representations, sort of representations that do not factor through a parabolic subgroup of GR. So they prove this, and so then coming back to our magical triples, the fact is that the classification that we gave for magical triples coincides exactly with the classification of positive structures, that is, the real forms for which you have magical triples that appear in the concept of magical triples are the same as they appear in the positivity structure. And the parabolic groups, PR, actually are related to the magical triple, to the nilpotent, nilpotent element defines a parabolic group and so on. And so in our paper, we proved that in these Cayley components that we have constructed using the Cayley map, there is an open subset of positive representations, right? So there's an open subset, and then we prove also that the representations corresponding to these elements do not factor through a parabolic subgroup of GR. So thanks to the theorem of Guichard, Laborie-Winchard, then we prove that then our elements consisted, our Cayley components consisted entirely of representations that are positive representations, full components, and therefore they are higher technical components. So this is how, combining all these works, we can not just classify the groups, but also give a full classification of this parametrization. What I mean by parametrization is this Cayley map that tells you these components correspond to some other moduli space, so things that are easier to study, for example, are less singular than a priori, you could think. But let me just finish by saying that, in fact, the original conjecture that Guichard, Laborie-Winchard was saying that the set of PR, positive representations, is closed in the character variety, not just in this subvariety that I was saying, but in the character variety. And this was just proved recently so this was proved for the SOPQ or POPQ by Byler and Pozzetti, using something called Collier lemmas, a generalization of a very well-known technique in usual technical theory. And it was announced some time ago that this could be generalized, and just a few days ago, a paper by these 5 authors appeared. This is the archive reference, proving that indeed positive representations are closed in the character variety. So positive representations define components. So if you want to prove that, you don't need Higgs values, but if you want to have a classification of this and also to study their topology and so on, the Cayley correspondence gives you exactly what are these components. Okay. Okay. Thank you.
I have a question. For the orbits that you have in the nilpotent cone, can you compute the dimension of these orbits?
Yeah. The dimensions of these orbits can be computed, and in particular, the dimensions of these magical ones, right? In some situations, we have been, for other applications, we have needed this kind of thing, but it's something that can be done indeed. Yes.
Do you have any guess that whether there are even? I mean, I'm suspecting that there are some symplectic lifts for some special Poisson structure that you will have there. So
yes, no, of course, yeah. They are, as you know, all this. In fact, is more general than, is not just for these magical things, right? The important orbits of the for a real group, in fact. And for the complex, but for the real group, I mentioned there was this constant Sekiguchi correspondence, right? That tells you that there's a one-to-one correspondence between nilpotent orbits in GR, right? And these nilpotent orbits in this space M, mod H, right? But the fact is, so Sekiguchi and Djokovic proved this. There is a one-to-one correspondence. But then Olivier Vicard suggested to Vergne that this could be, one could go farther and prove that there's not just a one-to-one correspondence in orbits, but an isomorphism of orbits of these asymplectic manifolds, right? And this was done by them and indicated, Olivier Vicard was indicating that using the NAM equations was actually the ingredient, right? And it turns out that actually this use of NAM equations is actually useful, also improving bijection, not just of nilpotent orbits, but yeah. So these are indeed symplectic manifolds, and you can as they say, this in particular, the constant Sekiguchi correspondence is an isomorphism, not just a bijection of orbits, but each orbit is isomorphic to the other asymplectic manifolds.
So the original Teichmüller theory so has to do with the moduli space for Riemann surfaces together with some choice of the basis of H1 and so on. So is this Teichmüller spaces, do they have some interpretation?
Well, this is the okay. In his first paper on this, Hitching, the 1992 paper, ended asking, okay, here are these spaces, but what is the significance? What is the geometric significance of them, right? And so this question, of course, is a question that is a natural question for all these Teichmüller spaces, right? So very soon after Hitching's paper, Goldman and others showed that, for example, for SL3R, the Hitching component had some interpretation as convex projective structures on the surface, right? And so other people sort of say, well, what about other higher rank groups, right? Initially were for the Hitching components, because the others were not available, right? The Maximal Toledo and so on. And so this is one of the most active areas of research, and in fact is where the action starts, right? Because okay, we have these spaces, but what do they parameterize, right? And so they indeed okay. Yishang and Binghard went on to show that in general, if you have a higher rank group, you cannot expect this to be some geometric structures on the surface, but some geometric structures on some bundle over the surface, right? And so they made some progress in that direction, but it's elusive, right? To sort of so this is one of the most active areas of research, right? What these spaces parameterize? This is in its infancy, right? Higher technical theory is now it's infancy, and there is definitely one of the most exciting areas. Or similarly, you know, one of the most important things of technical theory is the existence, yes, of a complex structure that is mapping class invariant. Right? So it's not the complex structure inherited via, I mean, all these higher technical spaces have a complex structures when you have chosen one on the Riemann surface. But no, the question is, is there any complex structure that is invariant under the mapping class group? This is another very active area of research. Some cases of rank 2 have been has been proved that indeed there is such a thing, and so so many of the usual Teichmüller theory people have been recycled now to higher technical people, sort of trying to generate the Collier lemmas. The Collier lemmas, that is one of the, I know nothing about Collier lemmas actually, but I mean, I was exposed to some talks, but this is something that really are exporting all questions and things to these higher technical spaces, and very exciting problems arising, right? From the point of view of Higgs bundles, as I said, what is the advantage of these parameterizations? These spaces, the fact that you are related to a group of smaller rank, It makes the study of the topology easier, right? Even the intersection cohomology, because they are singular, you can compute in many cases the intersection cohomology of the spaces and so on. But yeah, basic question is what is this spaces parametrize? This is one of the most exciting questions.
Well, I have actually two questions. Maybe one of them is very fast. But let me say, do you have an interpretation of the KD map in terms directly of the character variety?
That is a very good question, and you see Higgs bundles on the one hand, and these boundary maps, that is what you use, people like Inhard, Lavrie, and so on, etc., use with investigating the same animals, but from, it's like I always say, this is like two sides of the moon, right? We see just different two sides of the moon, and so we get inspiration from each other, and you prove this, I prove that, and I want to see if I can prove. So Higgs bundles are very good to prove global things like the topology, because the fact that they are complex of varieties, and in particular, very fundamental thing, is this CSR action that multiplies the Higgs field, and a Morse function that is the L2 norm of the Hitching of the Higgs field and so on, give you tools to compute topology. Now, Higgs bundles are not particularly good to say basic properties about the representations. But now, coming to your question, I will reformulate your question in a different way, which is the following. The Cayley correspondence gives us the moduli space of Higgs bundles, I mean these components, as moduli spaces of Higgs bundles twisted by some power of the canonical for other group and some holomorphic differentials. One side. On the other one, you have these boundary maps with the raw equivariant thing. It's clear that there is a one-to-one correspondence between these Cayley things and the boundary maps. Can you prove that directly? This is the challenging question. Years back, in the Hermitian case with Ignacio Mundet, we tried to do this, and we are actually discussing the other day that we should resume this question. One ingredient is that this Cayley partners, as we call this Cayley partners moduli spaces, have nothing to do as Higgs bundles with representations, because they are not twisted by K, right? But I mean, they have to do with representations via the Cayley map. But however, they have solutions to some Hitching equations. And so these solutions must be related to this boundary map. Can we find, so that is the one challenging problem. Once, if we get to understand that, we will have a nice bridge between these two theories. This is another of the challenging problem.
Actually, from my point of view, like the Hitching map has no correspondence in the character variety side. What is the Hitching map in the character variety?
Yeah, no, in the character variety, no, you cannot express it like that, but you can express very easily what is the Hitching component in the character variety. You can say the Hitching component consists of representations that can be deformed to the Teichmüller space of SL2R inside. Okay. Right? So that because SL2R is in SL in any speed group, right? Then the true Teichmüller space is embedded in the character variety, and you can characterize the Hitching component as those representations that deform. But that component is elements deformed. But yeah, but you're right, because actually the description of the Hitching component or all this Cayley correspondence depends on the complex structure. It's highly transcendental, right, correspondence. You cannot find explicit solutions, right? So this is one of the problems.
Let's thank the speaker again.